Hi, this is Module 4 of Mechanics of Materials Part 4. Today's learning outcome is to use the double integration method to determine the equation for the deflection of a beam. And so previously we've seen that we came up with a differential equation for the elastic curve of a beam, and we said that if we now have an equation for the moment along the beam, we can find the deflection by integrating this equation twice and using boundary conditions to find the constants of integration. And that's what we're going to do in this module. This is a worksheet where we're going to assume that E and I, or the flexural rigidity of the beam, is constant, and we're going to want to find the deflection of the beam as a function of x and then determine the maximum deflection and where it occurs. And so here's a demonstration of the system, and instead of having a moment at both ends, we're just going to put a moment on the right hand side where we have our roller constraint. Okay. What I'd like you to start off with is to solve for the reactions at the pin and the roller in this situation, and then come on back. These are the reactions that you should have gotten at the pin and the roller. And now that we have that, what I'd like you to do is to draw the shear diagram. And here's the shear diagram as a result. And draw the moment diagram. And here's the moment diagram that you should have come up with. Okay, now that we have the moment diagram, what I'd like you to do, we need an equation for the moment as a function of x. And so for this moment situation, or this moment diagram, go ahead and write an equation for the moment as a function of x. And this is what you should have come up with, so that we see here at x equals 0, we have a moment of 0, and then it's a ramp function, where at the end, where x equals L, the moment is equal to m sub n. And now we have our moment curvature relationship, and we have an expression for the moment as a function of x. And so what we're going to be able to do is to find the deflection by integrating it twice and using the boundary conditions to solve for the constants of integration. And so here is our expression, and let's go ahead and integrate once. And so we have E I dy dx is going to be equal to m sub n over L, and the integral of x is x squared over 2, plus we're going to have a constant of integration, which I'm going to call C1. And then we're going to integrate again to find the deflection y. So we have E I y is equal to now m sub n over 2L. And if I integrate x squared, we get x cubed over 3, plus now C1 times x plus C2. And so we've integrated twice to find the deflection, and we've introduced two constants of integration. And here are those results. What are the boundary conditions that we can use now to find the constants of integration? And what you should say is, well, we know the deflection at the left hand is equal to 0, and the deflection at the right hand, where x equals L, is equal to 0. So here's our expressions. Let's use the first boundary condition, y of 0 equals 0. That means that x is 0, this term drops out, x is 0, this term drops out, and we're left with C2. And so we find out that C2 is equal to 0 as one of our constants of integration. Now let's use the other boundary condition, E I y at x equals L equals 0. So that equals m sub n over 6L times L cubed plus C1 times L, and then we know that C2 is equal to 0. And so we can solve now for C1. C1 equals minus mn over 6. And then we've got L squared, but we have to divide by L, so it's just going to be L. So we get minus mn times L over 6 for C1. And so here's our expression for the slope now. EI is equal to this, and then this is C1. But we want to find, as our worksheet solution, the deflection of the beam is a function of x, and so that would be integrated, and we find out that this is the equation for the deflection. And so that's our answer. And we'll see you next time.